Hello again. So I'll just be giving another quick presentation, this time about my honors project that I did back in 2019. That was a part of the BGH with the supervision of Patrice and Luc Mani. So I looked at the influence of mechanical stratigraphy on the structural styles of fold belts using the Papuan fold belt as the main case study. So fold and thrust belts are areas of intense shortening that form in the four lines of orogenic systems all over the Earth through time. And in all these different places, you could see that the fold belts look really different to each other. They're all incredibly structurally diverse, and that's because of a multitude of factors contribute to the overall structural style of a fold belt and give each one its own structural flair. So mechanisms like the tectonic regime and plate kinematics the fold belt formed under to syntectonic sedimentation and erosion will have a large role on the overall structure of a fold belt. But some of the main first order controls include the amount of shortening, the level of basement involvement in inherited basement architecture from previous deformational events, and the mechanical stratigraphy, which refers to the relative strengths of the units making up the stratigraphic package. And that's basically the main mechanism we've honed on for my honors project. So the aim of this project was to explore the relationship between mechanical stratigraphy and structural style in fold belts, using the Papuan fold belt as the main case study. So we used the underrolled framework and ran two-dimensional models simulating fold and thrust belt accretion, and we calibrated our models with deformation styles from real-world analogs, and then we started tweaking the stratigraphy to understand how the material properties of different rock units will affect the overall structural style. So here's an example of one of those initial models where we were calibrating our models and trying to create a portfolio of experiments that were able to replicate structural styles of fold belts realistically. So here are some of the models compared to examples from the Angolan fold and thrust belt here with the large salt horizon. And then we've got some box folds from the Zagros fold and thrust belt up here. And in this corner is an imbricate thrust structure out of the Jura fold and thrust belt. So with the calibration out of the way, we were able to focus on the Papuan fold belt. So this is a picture of the Papuan landscape, and the fold belt is sitting underneath this canopy here. So you could see why detailed surface mapping or seismic surveys would be incredibly difficult. So the numerical modeling workflow could be really useful in places like this. Alright, so let's have a look at the stratigraphy of the Papuan fold belt. So we have large contrasts in the strength of the rocks here. Topping the stratigraphy when accretion began was the Darai limestone. This was a thick, competent unit, and it was the mechanically dominant one across the multilayer. In contrast, the stratigraphy also consists of these thick, weak muds and shales. These rocks deform like mush around the stronger limestone. Then there's also this unit of sandstone, which is a strong rock, but in this case the unit is relatively thin, so it may not exert a large amount of control on deformation style. So specifically within the Papuan fold belt, we were looking at the Gobi region. This is because of the interesting convergence between these two structural trends. These black lines show the Darai Plateau trend, which heavily involved the basement, whereas this red trend was thin-skinned and did not involve the basement. So we created synthetic models along where we also had various seismic interpretations. I'll briefly show models along the A and B transect in this talk. So here's the first transect with the two varying structural interpretations on the left. And our model is here on the right. So I'll run these. And so this one's got syntectonic sedimentation turned on, and this one's got it turned off. And you'll notice here in the model with the sedimentation, we don't form these faults in the blue layer, which was that strong limestone. Though when we left out the sedimentation, we do form them. So these are the two competing structural models. And based on our models, we would be more inclined to agree with this top interpretation because of the fault behavior in the Darai. But if the Darai was faulted, we would not necessarily expect to see them travel to this depth. As in our model, they nucleate in the strong limestone and detach at this interface here between the strong limestone and the weak mudstone. So here are models along the other transect where things are a bit more uncertain. So we're hoping our models could shed some light on the situation. The difference between these two models is the way we've implemented our isostasy boundary condition. One with a more regional approach and the other is more localized in an airy style way. Of course, you could see this had big implications. But overall, the idea is that these sorts of models could help guide structural models and interpretations. They could be used as a launching off of point, presenting a range of ideas that are mechanically sound, or could be used to discriminate between competing structural interpretations. So in conclusion, we've seen that mechanical stratigraphy plays a large role in the structural style of fold and thrust belts, and using a numerical modeling approach could help reveal the structure of the subsurface and enable us to be more certain of our interpretations. And to a certain extent, it could help de-risk some of the exploration in complicated areas like PNG. So let me know if you have any questions, and thank you for listening.